Hi, my name is Roberto Casati. I'm a researcher with a French CNRS, and I'm going to introduce some of the functionalities of a small piece of software that I produce with Glen Lomax. The software is called Astrini, and you can download it from the download page. It's a very small piece of software which can be used for educational purposes when trying to explain some of the basics functioning of the solar system and of the system Moon, Earth, Sun. We understand that there are some difficulties, and we would like to help teachers in presenting those simple facts. Astrini is a bit different from other software like Celestia and Stellarium. It's not a virtual observatory. It is a model, and as a model, it can be parameterized. That is, you can change some of the parameters in the model in order to show what the phenomena actually are or are not. So when you open the software, you get a screen like that, and it might be or not moving, but you can do a number of things just to get started. One is to display some of the hidden features, like marks for the orbits. You can have or not stars. I prefer not in this demonstration. And you can also add shadows that are cast by the moon and the earth, originated by the sun. As I said, this is a model, so it is not supposed to be a representation in scale. If you want to see the actual scale, you can click on scale on the left, and you see what the actual distances are, so very hard to work with. So we prefer to use this scaled up version, in which it is easier to see some of the phenomena. Now, Astrini, like many other softwares, allows you to go to different places and look at the world and the universe from those different places. So you can go to the sun, for instance, and if you go to the sun, this is the Moon-Earth system, as you can see it from the sun. But you can also go to the moon or go to the Earth and look at other objects which are around you. Well, you can decide which object you are looking at. For instance, if you are on the Earth, you can look at either at the moon or at the sun. And so you have a different perspective on the universe and different objects in your field of view. But you can also do the same if you go to the sun. You can decide to look at the moon or to look at the Earth and see the relative moments in terms of the body you're looking at. Suppose that you look at the sun and that you put yourself in the external mode, that is, you're outside, like a cosmonaut, looking at the system from the outside. So the real pedagogical part of it, after having got acquainted with some of the basics, is to modify some of the parameters. Actually, Astrini, as you see it now, presents a false view of the Earth, Sun, Moon system, a view in which everything has been straightened up so that the orbit of the Moon is in the same plane as the orbit of the Earth around the Sun, and the axis of the Earth is normal to the orbit, is normal to the ecliptic plane, which is very convenient in order to show how it works, but it is not the truth. So the module that we present is very simple. It's supposed to be run by a teacher who introduces his or her pupil to elementary astronomy. It consists on first describing what is on the display now and analyzing some simple facts, and then changing the facts so that they come closer to the actual situation. So let's start from another couple of possibilities for parameterizing Astrini. You can speed up or slow down or pause the movement of the celestial bodies. So you can accelerate them or slow them down. And you can actually also run them in the reverse. But maybe this is not what you want to do. And you can also do something else, which is to jump forward. You can jump forward by a day, so the Earth makes an extra spin, or you can jump forward by a month, so it's about an orbit, circling of the moon around the Earth about, or you can also move forward about a season. So these are possibilities that allow you to navigate the year, navigate in time. Now, the important part of Astrini is that you can modify two important parameters. One is the angle at which the orbit of the moon, the inclination of the orbit of the moon relative to the orbit of the Earth. So this is about the actual change, a few degrees, but you can increase the change so that you can see it better. So by so doing, you can point to a very simple fact. Suppose you're not presenting an inclination of the orbit of the moon relative to the orbit of the Earth. So each month, the moon is going to be between the Earth and the Sun, and each month, the Earth is going to be between the moon and the Sun. So each month, you will have a solar eclipse, and each month, you will have a lunar eclipse. And this is particularly clear if you change your point of view. For instance, if you go to the Sun and look at the situation, maybe slowing it down a little bit, you will see from the Sun's viewpoint, each month, the Earth is going to hide the moon. And so this would be a situation in which you have an eclipse of the moon. So that I pause the system, and if you now go to the Earth and look at the moon, you will see that the moon is, so you go there and look at the moon, you will see that the moon is in the shade. If we let the system go from here, at some point, the moon will get out of the shade of the Earth. So the same, if you go to the Sun now and you have a system restart, looking at the Earth, you will see that after a while, the moon is going to be interposed between the Earth and the Sun. And in this situation, you would have an eclipse of the Sun from the viewpoint of the Earth. I pause the system. So let's look at what happens when you go to the moon and look at the Earth. You'll see that the moon is casting its shadow to the Earth. Of course, this is out of scale because the system has not been reproduced to scale. And you can have the system evolve and see the different position of the Earth, of the moon's shadow on the Earth. But you can also go to the Earth, and in this case, look at the Sun, and you will see. Let's go a bit in reverse. You will see that you have an eclipse of the Sun. Actually, the system has been calibrated so that you will see the total eclipse up to scale from the Earth viewpoint. So the question, the pedagogical question to be asked now is, why don't you have this particular configuration each single month? Because this is what happens when you have the two orbits as perfectly coplanar. The answer is in the fact that the moon's orbit is actually tilted. So sometimes when the three celestial bodies are in the same plane, they are actually not aligned. So go again to the Sun, and you can see that you're not having an eclipse of the moon because the orbit of the moon is actually tilted. And so the shadow cast by the Earth is not intercepting the moon. If you go to the Earth and look at the moon, you see that the moon is outside the shadow of the Earth. So this is the first piece of information that you can deliver by altering the parameters. We go back to the external view, and we reproduce the same for an eclipse of the sun as seen from Earth. You will see that when the moon moves and is in the same plane as the Earth and the sun, its shadow will not intercept the Earth. So we go now to the Earth and look at the system, and we see that the shadow of the moon is not hitting us. Or we go to the sun and look at the moon Earth system, and we see that the shadow of the moon, actually you cannot see any shadows from the sun because the sun is casting shadows. It's like a flash photography. It is not casting its shadow on the Earth. So let's go back to this situation, which allows us to show another type of manipulation that you can do in Astrini, and this is most easily seen from the sun. From the sun, the manipulation consists in changing the tilt of the Earth axis from normal to the ecliptic plane to tilted, which is the actual situation. So do not consider the moon anymore, just look at what happens to the Earth when you look at it from the sun in a situation in which the axis is not tilted. So each day, the cycle of day and night is such, if the axis is not tilted, that on each point of the planet, the day has exactly the same length as the night. And it is as if we are in a constant equinox. If, on the other hand, the axis is tilted of its actual inclination, 23 and some degrees, as soon as time goes by, you will see the different portions of the Earth are more visible from the sun. So the days are passing, and you will see that more and more of the northern hemisphere, and actually of the North Pole is visible. Month after month, we can accelerate that a bit. And at some point, the situation reverses, and more of the southern hemisphere is visible from the sun. So the sun is our source of energy, and this small tilt of the axis, as far as the Earth progresses on its orbit, is enough to cause different portions of the Earth to be lit up by this source of energy. So night and day have different durations on different portions of the Earth, and the sun's rays are hitting at different angles, which explains the difference in light and in heat, or cold and hot, along the year with the seasons. If we are back to this impossible situation, non-factual situation, night and day are always the same on Earth. So Astrini is a very simple piece of software. As I said, it is not supposed to teach the whole of astronomy. It is supposed to present a simplified version, a model. And the advantage of having a model is that you can toy with it, change some of the parameters. And by playing with those parameters, we hope that we'll be able to convey the sense of the phenomena, especially as it concerns phenomena which are apparently very difficult to understand in primary and secondary school. Thank you for your attention and enjoy.